Hello, my name is Kevin Modi. I'm a lecturer in School of Physics and Astronomy, and I'm a researcher in quantum information theory. For the next few weeks, I'll be lecturing you on electricity and magnetism subunit. In the first week, we're going to talk about electric fields, electric flux, and Gauss's law. This first video is going to introduce you to the basic ideas of electricity, and we're going to talk about what charge is and how Coulomb's force works. So I'm going to try to disappear a little bit myself, and I'm going to move around on the lecture and put myself at the concept that I'm discussing. So stuff that surrounds us, all of the objects have mass and volume, and another essential quality they have is charge. And this is because everything is made of electrons, protons, and neutrons. And electrons are the fundamental particles that have negative charge, while protons are the fundamental particles that have positive charge. The charge of an electron is 1.6 times 10 to the 19 coulombs. That's negatively charged. Proton has the same charge, but it's positive. This is a very small amount of charge. Nevertheless, there are many, many electrons in even a single gram of stuff. The number of atoms in 1 gram of stuff is about 10 to the 23. And each atom has tens of electrons, so there are many, many electrons. Nevertheless, most stuff around us is electrically neutral. So let's consider two objects, a piece of wool cloth and a plastic rod. Both of these things are made of atoms, and each atom has some protons and some electrons. Since protons have positive charge and electrons have negative charge, the net charge for each object is really zero if the number of protons and electrons are the same. However, we can rub the plastic rod with wool cloth, and when we do that, some of the electrons on the wool cloth will remain on the plastic rod. And so if we look at the net charge, we will have some net negative charge on the plastic rod, and we will have net positive charge on the woolen cloth. The magnitude of both of these charges have to be equal and opposite, and this is because charge is conserved. Now, how can we detect this? How do we know that this is in fact true? Well, we can do an experiment with something called an electroscope. We can take this plastic rod and bring it in touch with the sphere that is on top of the electroscope. It's made of metal, and then there is a metal bar that runs down, and then there are two golden leaves at the bottom. These are very thin leaves. They're like aluminum foil at the bottom. Now what happens is, initially the leaves are just facing down like this, upside down, and they're touching each other. But when the charge is placed on the sphere up top, the leaves will separate. And we're going to discuss why that is. Before we do that, let's talk about what kind of properties insulators and conductors have. So insulators, such as the plastic rod or the woolen cloth, are made of atoms that keep their electrons to themselves, while conductors are made of stuff where atoms share electrons. So an insulator effectively means that electrons are confined to a very specific region near the atom, and they're not free to run around. However, we can rub the woolen cloth and the plastic rod together to strip some electrons from the woolen cloth and place them on the plastic rod. But once they're on the plastic rod, they sit where they are. Now, when we bring that plastic rod with excess electrons in contact to the metal surface, these electrons will jump onto the metal surface and run around freely. And because electrons don't like each other, which we will discuss in the next slide, they try to get away from each other as much as possible. And we'll come back to that idea in a second. So, let's think about mass and the gravitational law. If you have two masses and the gravitational force between them is attractive. This is in fact opposite of what happens for the electric force. Two charges that have the same sign, say two positively charged or two negatively charged particles, will repel each other. They don't like each other. While two oppositely charged particles will attract each other. And the force between these two charges is given by Coulomb's law, which looks a lot like gravitational law. And K here is the Coulomb's constant, and here it's units and value. And K often is written as 1 over 4 pi epsilon naught. And this turns out to be a more convenient way of writing this constant. And initially Coulomb had written it as K, and then later on it was revised to 1 over 4 pi epsilon naught. I mentioned this because you might see this constant written both of these ways in the lectures that you'll be in the videos that you'll be seeing for various lectures. So let's go back to our experiment where plastic rod was charged and then brought in contact with the metal sphere. Now what happens here is that electrons jump onto the sphere, but they don't like each other, so if there are few electrons, they're going to try to get away from each other as much as possible. And the best place for them to orient themselves is going to be on the surface. Since they're free to move around, it turns out that one can show that the optimal configuration for all these electrons is to distribute themselves on the surface. Now, some of the electrons will get onto the golden leaves down below, and these electrons will repel each other. And if the leaves are together, as there are electrons on both leaves, they will repel each other and the leaves will move apart. And this is an indication for us that there is charge on the electroscope. Now, suppose instead of bringing a plastic rod in contact with the electroscope, we bring in a metal rod that has net positive charge. In other words, it has fewer electrons than the total number of protons it has. And we bring it close to the electroscope. We don't touch it, but we bring it only close to the electroscope. What happens then is there will be some electrons on the electroscope that will be attracted to the net positive charge on the metal rod, and they will come to the top on the top of the electroscope on the sphere surface. This in turn generates generates a net positive charge down below on the leaves, and the leaves will separate. So even without touching the metal rod, we can determine if it has some charge on it. Now, in the next set of lectures, we're going to start with Coulomb's force and talk about electric field and how the force is related to the electric field, and from there on move to Gauss's law.